All right, hi. Thank you for coming to Math Club Presents. Nicholas Pasquale, I am he, and this is what's really going on with numbers, getting to the base of things. What I would like to talk about for this period of time is just kind of like what is going on with the way we write numbers. And I thought a good introduction just to get us, fluent with something that we're very familiar with already is just to talk about how do we know when a number is divisible by another number. And I'll use that to lead into what this idea of base means for numbers. All right. And so at the end, we'll do some examples with math in a different base. And so if you've heard of, say binary or hexadecimal, you may be aware that we use a base 10 system typically, but there are many times where we want to rewrite a number in terms of this other base, right? So what's really going on here? I thought we'd start off with something that looks fairly familiar, all right? Divisible by 2, right? Think to yourself here, which of these numbers is divisible by 2? Right, and then when we say divisible by 2, we also mean a multiple of 2, right? Like 2 times something would give you this number. Which one of these 4? Right? 462, right? So what's the rule, right? We all know when a number is divisible by 2, it ends in a 0, a 2, a 4, a 6, or an 8, right? So that's like the easiest one to spot when you have an even number, right? And so, why does that rule work? And so getting to the heart of why this rule works will help us understand the next few rules and ultimately what base will mean for us, right? So we're going to talk about mostly 3-digit numbers today, but of course this works for 2 digits, 4 digits, 5 digits. So I'm going to write 3-digit numbers in the form ABC. All right, and the A and the B and the C are the digits, right? They're 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? There's 10 digits if you start with 0. What a coincidence, right, with our hands. So A we call the hundreds place, right? B is in the tens place, and C is in the units place, right? This is just our common vocabulary that we were taught to use with numbers, right? And so we can rewrite the number ABC as 100 times A plus 10 times B plus C, right? This makes it look more like an algebra expression now. And actually that is really what we're going to be doing here, is talking about what is basically this polynomial where instead of X, we're using 10, right? So interesting tie-ins to things that we've learned before that maybe we didn't mention, in regards to arithmetic. All right, so an example, right? 376 is 300 plus 70 plus 6. I think it's pretty straightforward. So good refresher, right? So why does the divisible by 2 rule work? Well, notice that if you have 100 and a 10, those 2 numbers are always divisible by 2, right? So it's just a matter of, is that last digit divisible by 2? And the reason we care about that last digit is because of the distributive property from algebra, right? We want to be able to distribute a 2 through each of those 3 places. So that last digit, because it doesn't have a 10 with it already, right? It's just a single unit digit, has to be one of the ones that 2 goes into. All right, so it's a pretty neat little rule from algebra, really, right? Let's try some more here. Which of the following numbers is divisible by 10? Oh, 10's a larger number, but I think we can agree that the rule might even be easier to spot, right? For 10s. And so 710. Well, what was the rule, right? What has to be true about a digit ABC? What does that C need to be? That's the rule we're thinking of, right? That C has to be a 0. I'll go back and we can look, right? None of these are divisible by 10. The 3 in the around the 710, but only the 710, right? That last digit has to be a 0. And so that's because if that last digit is a 0, right, it's AB0, AB0, then you can factor a 10 out of the 100 and the 10 on its own, right? So that makes this a nice distributive property issue again. All right. So I think we're ready for some more advanced ones already, which are divisible by 5. Oh, I have multiple of 2 here. I'm sorry, that should say multiple of 5. You can tell I copied and pasted a slide. Which one? Oh, it's a trick question though, isn't it? There's 2 of them. All right, and that's just because 10, right, is already 2 times 5. So 5 gets 2 of those digits, right? And the why does that rule work is similar to the distributive property reasons that we saw for the other 2 rules. So let's see. Are there other quick to spot divisibility rules? Yeah. Well, how about divisible by 3? All right. I picked some 2-digit numbers here, so maybe that they look. You'll see one that looks familiar, right? Which of these numbers is divisible by 3? Right? 3 times 9, right? Okay, no problem. That was 2 digits though, right? Let's do some advanced work here. Which one of these is divisible by 3? Oh, without get your TI ready, right? give everyone a minute here to appreciate these numbers. All right. Did you spot the one that was divisible by 3? That's kind of a surprise, I thought, for me, right? So you can see I'm trying to distract you, right? I put 3s in the last digits, a 6 in the last digit, but actually none of those are divisible by 3. Not evenly if we're talking about like not having fractions, which we are. 111. Huh. All right, here's some more. Which one of these is divisible by 3? Oh, also, I think a surprise, right? Because maybe I think that's like a cognitive trick. That one's clearly divisible by 5, so I'll move on, right? Look at the other ones. I don't know. That's how I thought about it. 10, right? Yeah. But no, this is the one divisible by 3. All right. So I'm going to show you how we can know very quickly which number is divisible by 3. All right. So here's another. Which of these is divisible by 3? They all are. These are all divisible by 3. And I think that this example might help us start to formulate like what the rule happening here is, right? Notice that all 4 of these numbers are the same 3 digits, just rearranged, right? So the divisible by 3 rule doesn't have anything to do with the places this time, not directly. All right, we'll see that it does ultimately, but it's not about which one the last digit is, right? It's about what all of the digits are. So, here, what's the rule here? Here are some of the ones that we've seen now that are divisible by 3, right? And so we want to start thinking about like, how are these digits resulting in this rule here? And so did you notice that when we looked at those digits, right, all of those digits add up to a number that is already divisible by 3, right? 2 plus 7 is 9. 1 plus 1 plus 1 is 3. 1 plus 0 plus 5 is 6. 2 plus 0 plus 1 is 3, right? 1 plus 2 plus 0 is 3, right? So that is the rule that we're using to quickly determine if a number can be divided by 3. You add up all the digits, A plus B plus C, and you, I wrote 2 here again. And you ask if that number is divisible by 3 itself. It's a really interesting rule, right? You wanna see that again in action here, right? So now check, right? We call this process the digital root, right? So 1 plus 0 plus 5 is 6. 6 is divisible by 3, no problem, right? 5 plus 5 plus 9, well, that's 19. And even if you didn't know if 19 was divisible by 3, you can do 1 plus 9 again and get 10, and 10, and then 1 plus 0 if you want. You can keep going all the way down. Any number, right? 3 plus 7 plus 0 is 10, not divisible by 3, right? 1 plus 0 is 1, so that 10 is not divisible by 3 either, right? So as long as you know 3, 6, and 9, right, and you add up all those digits to get that root repeatedly, you can determine very quickly if a number is divisible by 3. That rule, though, is very different from 2, 5, and 10, right? So, why that rule is so different is what we're going to see in a minute. But ultimately, it has to do with the fact that the way we're writing the numbers is in what we will call base 10. So a base 10 number, which is divisible by 10, well, it's based on the place values being divisible by 10. But 10 is also divisible by 2 and 5, right? So the 2 rule, the 5 rule, and the 10 rule really did look similar. The 3, though, 3 is not a factor of 10. So the 3 rule is going to be quite different. All right, so why does the 3 rule work? All right, and to talk about why the 3 rule works, I want to start maybe talking about what the difference between an amount is versus how we write the number for that amount. So here I have a bunch of pips, right? And this is called the set theory of arithmetic, by the way. Can you make 3 sets of these pips that have the same amount in each of them? And that's what we call divisible by 3, right? And yeah, indeed, I can find 3 groups that have the same amount of pips in them. So this amount is divisible by 3. Notice it has nothing to do with how we write the number. It is an innate quality of the amount, right? So, but nonetheless, we do write the number as 72. This happens to be 72 pips. Maybe I should have told you that. I apologize if you were trying to count really quickly. But yeah, this is 72. And of course, you might have noticed that I made one string of 12 pips and then just copied and pasted it 6 times, right? So clever use of copy and paste there. But yeah, so 72. But not everyone writes that number 72, right? Not as 7 and 2, right? There are other bases, binary, for example, but there are also other number systems that don't necessarily use a base. So here's 2 examples, right? Historical examples. Imagine you're a Roman, right? And you're going to write 72 as LXXII, which is 50, 10, 10, and 2, right? Well, 7 plus 2 is 9. So the divisibility rule we talked about works for 72. But L plus X plus X plus I, that means that's nonsense, right? So that rule doesn't work. And then here, see our Mayan system, right? The Mayans use a variation of base 20. So these 3 pips on the top each represented 20. So it's 20, 40, 60. And then in the bottom here, these are the ones. A bar is 5, so it's 5, 10, and then 2 more is 12. So 60 plus 12 is 72, right? But there's no way to grab, is this number divisible by 3 just looking at it, I can't, I don't. So that those division rules that we use for our own numbers are for base 10 representation, right? Any other way to represent these groups of numbers, the divisibility rules are different. So I thought that would be just a really fun lead in to what base does, really, right? Writing a number in terms of a base means that we are representing that that amount with digits, and the digits will have properties with divisibility based on the base, right? The number itself, the amount itself doesn't change, right? It's just that what we can do with the digits or the symbols, right? Those change. So that's kind of one of the things about like what's going on with arithmetic. Why does arithmetic work, or how does it even work? Well, it's specific to the way we even write numbers. Before Fibonacci popularized the Hindu Arabic numerals, and Europeans were writing the Roman numerals out. They and cultures and other cultures on the planet, like they had to use abacus to add up or subtract large quantities. And so that was like the real benefit of writing numbers with these Hindu Arabic numerals, is we can do math really quick on paper now, right? And so good news for us, I suppose, but we chose 10, right? So we have a 10. So here's what's going on with 10, right? We wrote A, B, C, right? So we said the A is the hundreds place, B is the tens place, right? C is the ones place up here. And just that base 10 is really the fact that 100 is 10 squared, 10 is 10 to the first, even 1 is 10 to the 0, right? And I think this makes it pretty obvious that this will work for 4-digit numbers, right? Because we would have 1,000 to be the next place. So we'd have 10 cubed, right? And we just keep increasing our numbers that way, right? But we use base 10. If we switch the base, we're not going to have those nice divisibility rules anymore, right? So here's my little demonstration for why the 3 divisibility rule works. All right. You remember long division? Does that give you nice warm feelings of having to do math by hand? So here I wrote ABC, but I made sure to keep their place values. And actually, I recently reviewed long division with polynomials. So, maybe this will look similar to that because we have some symbolic, logic going on with our division algorithm, right? So, how do we do division? Well, 3 goes into 100, 33 times, right? But then we subtract the line, right? So we're going to have one of those A's left over. And of course, everyone's favorite part of long division, right, is bring down the 10b, right? So we're bringing that down. And see, how many times does 3 go into 10b, right? Well, 3 goes into 10 3 times, right? So 3b is what we need up there. But 3 times 3 is 9, right? You see how we're always like 1 short. This would work if I went to the thousands place also. If we had 1000d, 3 would go into that 333 times to give you 999, right? So we are always this 1 short with the 3s. And so what's that thing at the bottom of long division called? That's called the remainder. If you want to divide something and not get a fraction, right, that remainder down there needs to be 0. But since this is ABC, it could be any set of digits. We want that to be divisible by 3 as well, right? So that's really what it comes down to is the remainder A plus B plus C, is that also divisible by 3, right? So that's required for a number to be divisible by 3, which is why we can quickly just check. And so, when we said like which of these numbers are divisible by 3, and we saw all those examples, we said, oh, we add up those digits. We didn't say we're checking the remainder of long division, right? Can you imagine if I said really quick, check the remainder from the long division of this? Like, but now that we've used the A, B's, and C's, we can see like the magic happening, but what was going on behind the curtain with the rule, right? It's just check that we're checking the remainder. Is this fully divided, right? Yeah, and so I'm going to stop with 3 because you might be wondering, oh my gosh, are there more divisibility rules now? Yeah, there are, for 4, for 8. And actually with the long division process, you can pretty much make a rule for any does the following number divide. Just some of them have really terrible patterns, or maybe a sequence that takes a very long time to even see a pattern. 7, for example, I mean, divide divide 1 by 7 in your calculator, right? 1 by 7 has a terrible decimal, and that's going to show up in the long division as well. So 3 is like a really nice one to remember, right? But 11 is a nice one also. 9 is very similar to 3, but like 7, seven's it's harder to remember the rule for 7, and you can do the long division to see what it is, but it makes no sense. And so we just would divide by, it's sometimes faster for 7 just to do it right away. Of course, most of our work these days is not us actually doing the division, right? So this is a good kind of theoretical playground here to talk about. But you can look up many other divisibility rules and see what they are. For 2 is the last digit divisible by 2. 4 is the last 2 digits divisible by 2. Or by 4, sorry, or last 2 digits divisible by 4. And why is that? You can explore the why is part by using the long division algorithm. So I'll show that again one more time. You can do this for any digits and see what the result is. You can even do it for the rules we've already seen for 2, 5, and 10, and see how this is a little different, but yet comes across or gets to the same result, right, that we had before. So yeah, it's a pretty fun little demonstration, especially because of all the tie-ins, right? This is division, but we kept some variables in there. So that means we are using algebra really, right, to explain what's going on with arithmetic, which is ultimately why we have variables in algebra, right, to represent any real number, so that we follow the rules of arithmetic with these symbols. And this is a nice tie-in here, I thought, to some past experience. But I want to talk about what bases are, right? So that was a very long introduction into things that happen special because we have base 10, right? Base 10 gave us these special things. But what does it mean to have a base? Like, I think what we need to explore then is, what does another base system look like? So here is kind of how I think about what base it means. Here I have my 10 to the 0, and that's 1. So I think of these as packaging problems. And I can't take credit for this idea. This is from my advisor in Boston, Carol Findell, great doctor in math education. But really what we're doing when we do arithmetic is we're repackaging, right? So I have all of these small boxes, but if I have 10 of them, I can upgrade them to a long box. And if I have 10 long boxes, I can upgrade those to a flat box, right? If we have 10 of those, we can upgrade those to the big cube over there, right? So in this sense, we have like how many of the small packages can make a big package, right? If you have 4 of these and 6 more of them, right, then we get the new place. We get the 1, 0, right? That 1 shows up in the tens place to indicate we have a 10 now, right? If we have 10 of these, then that 1 shows up over here in the hundreds place, and we have 100 show up now. So that's how I think of digits in our numbers, right? Is that just tells you how many, 376. I have 3 of the flats. I have 7 of the longs. I have 6 of the little short ones, right? So in my mind, that's all we're doing is packaging these amounts. So it is about the pips, really. How many of these pips can go in the large packages, right? What's left over, I put them in a small package. What's left over, I put them in a smaller package. So so I thought what we would do for the second half of this little demonstration is we would do some just arithmetic with base 5. All right. So and I'm very proud of this graphic. All right. It was I had to make the long, right, half as long, which changed the shape. Anyway, I'm very proud of myself. And so yeah, in base 5, All right, if we have the number 111, right, which previously meant 111, in this case it would be, we would have, in this case it means we have 125 and 1 5 and 1 1, right? So so what I'm going to do is share my notepad screen here and just kind of like show us like how to think about a base 5 number, and then we'll add a couple and see how adding is different, and maybe we'll even subtract one. All right, I wanted to try to do some problems that use words that you were probably told in elementary school, or maybe in which we still use in even in college math, right? Like carry the one, right? Borrow. What does borrowing mean? So I thought we would do some examples with those. Let me share my notepad here. All right, so let's do some base 5 arithmetic. And again, we're just thinking of this in terms of packaging in fives. So let me just write some numbers first of all here. So let's do base 10 number, just so we have a comparison. It's like, I'll just make one up, 235. And I'm going to write a little 10 down here now, like as a subscript to indicate is base 10, right? This is 200, right, plus 30 plus 5, right? Or in the like base representation, this is 2 times 10 squared, right, plus 3 times 10 to the first, plus 5 times 10 to the 0, right? So again, this is our base system. Notice, by the way, if we replace the 10 with an x, we are talking about quadratic equations, right? So this is an interesting thing to note that is a important part of abstract algebra for you math majors. So let's write a number in base 5, the same number. It will look this, sorry, the same digits. Sorry. Oh, no, can't use a 5 yet. Sorry, let's talk about base 10. It's good for me to review this too, right? So base 10 has the following digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but not, and that's it, because what's the next one? 10, right? Oh, but that's 2 digits now, so we stop. But with the 0, 10 digits, right? So base 5 has the following digits, right? So this should only have 5 digits then. 0, 1, 2, 3, and 4. All right, so that's why I can't write this number with a little 5 beneath it, because 5 isn't an allowable digit for base 5. All right, so let me write a different number with base 5 then. Let's write 2, 1, 3. I'll put a little 5 subscript down here. So what does that number even mean? That's 2 times 5 squared plus 1 times 5 to the first plus 3 times 5 to the 0, right? So that's, that's 2 times 125, sorry, times 25 plus a 5, right, plus a 3. So that's going to be 58, right, in base 10. So remember, this is the same number of pips in our set, but the digital representation in base 5 is 213, but the digital representation in base 10 is 58, right? So same amount, very different ways to write them, right? And so I thought we would do some adding here in base 5. Should we review adding in base 10? No, you don't need to review adding in base 10, right? You got it. So let's do some problems here. Let's do I'll just make some numbers up. I don't want to be too crazy with this. So let's just do like 2, 2 base 5. All right, plus let's do 1, 1, 3 base 5. All right. So, and just adding it, right? And I'm just gonna draw a line here to like separate the places, right? This is the units place, right? That's the little box, right? This is, I can't say the tens place anymore because it's base 5, right? This is the 5's place. But in my graphic I used earlier, right, that was the long box. So remember, anytime we get 5 of these short boxes, we can convert it to one of the long boxes. All right, so that's really what we're doing here. So we can do 2 plus 3 is 5, but that's cheating, right? If I do that, because that's not one of the allowable digits in my base representation for 5, right? So instead, I'm going to say, oh, I'm going to convert now, or we can say we're going to trade, or we're going to repackage, right? So this 5, right, becomes a long package. And how many short packages are left over? In this case, 0, all right? So we got to convert from our short packages to our long packages. And now let's add up how many long packages we have. We have 2, 1, and 1, right? Oh, that's 4. So I have 4 long packages and no short packages, right? So there we go. So 2 plus 2, 2. We don't say 22. You know, this is hard when we teach this. We do have a course that goes over this specifically called Math 12. And it's a challenge in that class to talk about base arithmetic because everyone wants to say 22 when they see this. But you know, what does the word 20 mean? It means 2 tens, right? 2 tens, like slurred together. Well, we don't have 2 tens, right? We're talking 5s. So we try to say just 2, 2 and 1, 3, but you can see how awkward that is. Very often people will still say 22 base 5 and we know what they mean. But you know, so but imagine you were doing something like this and your friend walked by and saw you with this answer, you know, you would have a lot of explaining to do, right? How did you get 40? How did you get 40 when you added these up? So let's try some more, I thought, of these base 5 conversions. All right. We'll switch to black here. So we have 2, let's do 2, 0, 2 base 5. All right. Oh, 3 digits now. All right. Graduating us into some advanced stuff. And let's do 1, 3, 2 base 5. All right. So I add these together. And again, I'm going to separate the places first, just to make sure we don't make any mistakes. So, and other than that, right, this is very much like adding how, you know, we're frequently shown the standard addition algorithm is what we call it now in math ed, right? So, you know, 2 plus 2 is 4. Is that an allowable digit in base 5? You know, yes, yes, it is. So that one's okay. So we get to leave the 4, right? 0 plus 3, oh, that's just 3. That's also allowable, right? No problem. But remember that 3 means we have 3 5s, right? These are the longs. And then 2 plus 1 is 3, also not a problem, right? But this is base 5. Now back to if your friend walked in, right, and saw you with this, they wouldn't even suspect something was different, right? Like, ah, good. My dear friend knows how to add. I was worried, but that one's fine, right? But the number being represented here is actually very different, you know? So if you were to tell your friend like, hey, yeah, it looks correct, but you know, just know that this is the number that we're talking about, right? 75 plus 15 plus 4. Now I'm doing some mental arithmetic. That was a bad mistake. Like that's actually this number in base 10, right? In base 10. And then now it looks like you've lost your mind. And Frank, and you know, I mean, think about when you do math, right? When you're doing your math around your friends who have, you know, maybe not your major, right? And you do some algebra, you do some calculus, and they see what you're doing. It looks completely foreign, right? It looks alien. Like, what are you doing? Where are these symbols? So, but this is arithmetic, and really this is just goes to show you that it's not the higher levels of math that look like they came from outer space. All right, even the most basic math can look like it came from outer space. It's the complexity that we're putting in this, right? So that, in my mind, that's what it is to study math, is to look at even simple things and really see if you can divide it up into even more parts to see what happens if you rearrange things. Let's do an example with a lot of unit conversion, right, or repackaging. All right, so again, we're repackaging. All right, repackaging. And I trick students in Math 12 and in pre-algebra to do base arithmetic by just having warm-ups that are packaging. I'll say convert all of these small packages. I'll say, like, today we have, I'll say today we have 23 short packages, and every time you have 5, you can upgrade it, right? And that will be like the warm up. And so like, well, how many groups of 5 are there in here, right? Well, 23. So there's at least 4 groups of 5, right? 5. So there's 4 longs here, right? And then there's 3 left over, right? So very quickly they can do, we can all do base arithmetic by just thinking of it as putting it in different sized boxes. And so anyway, when you see binary and hexadecimal and so computer science or whatever, like, all we're doing is just using different size boxes. If you want to be really fast with the arithmetic, you have to do a lot of it to get used to the rules that you are used to in base 10, right? What's 4 plus 3? It's 7, right? But without that constant experience with other bases, it seems like a mystery. So we just keep practicing this, so here's one. We're going to add 233 plus 315, right? So 3 plus 3, and again, it's cheating, but I'll write 6, right? Because that's the one I know. I know 3 plus 3 is 6. But unfortunately, that is not in base 5. I have to convert. So I have 5 shorts, right? So I will give myself a long for that. I'll go down diagonal here. I'll give myself a long. I have 1 short left over, though. All right. And so now I'm going to add up my longs, or the 5s, right? Here's my shorts, my longs, and we have our flats, right? So I have 3 plus 1 plus 0. Oh, that's 4, right? So that's all fine. I didn't give myself a long. There's a comment in the, I had a moment of don't know what that moment was called. A moment of Zoom teaching all day. That's what it was. Yeah, sorry, 1 long. Thank you. Good. Thank you, audience participation. Indeed, I have 1 long, right? Because 6 of the shorts turns into 1 long and 1 short. All right. I think in my mind I did write that, but obviously I did not. 1 1, right? Okay, so now 3 plus 1 plus 1. Oh, that's 5, right? And so 3 plus 1 plus 1 is 5. We're not allowed to use 5. That's not one of the digits. So got to repackage, right? 5 of these turns into 1 flat, right? And I don't have any of the longs left over. All right. So far, this is what we got, right? We have that 1 left over in the shorts. We only have this 1 now in the longs because we had to up package. Oh, nope, sorry. This is my color coding got off. 3 plus 1 plus 1 is 5. I should draw a line here. So yeah, so we don't have any longs now. And now let's do the flats. 2 plus 3 is 5 plus 1 is 6. Oh, not allowed to use 6 though. So got to up package that. 6 gives me 1 long, but also 1 short. Well, it's not even a long anymore, is it? It's the cubed one. All right, it's that new placeholder. And then we have a 0 and a 1. All right, good times. So in summation, 2, 3, 3, 3, 1, 3 in base 5, right, is 1, 1, 0, 1 in base 5 when you add them. All right, pretty intense. All right. I should draw that line every time we add together. But that's why I like, that's why this idea of place value is so important, right? Because you want to make sure that you are using the correct number of your packages or your base places, right? And then adhere to the digits you're allowed to use. Shall we try subtraction? Yeah, let's do some subtraction. Well, keep this fairly simple here. All right. And interestingly, I'd encourage you all to maybe try this with binary. All right. Binary, famously, you just get to use 0 and 1, right? And just add a bunch of zeros and ones. Right. Well, 1 plus 1 is 2, but you're not allowed to have 2, right? So you have to up package this. It's a 1 and a 0, right? And you can kind of see how for binary specifically, you do 1 and 1 is 2, but you can't use 2, right? So you have to up package it. 1 plus 1 is 2. Oh, can't use 2. You have to up package it, right? 1 plus 1 plus 1 is 3. Well, that's way too much, right? 3 gives you a 1 and a 1 here, right? So, you can start playing around with these higher bases here. 1 and a 1, 0, 0, 0, right? To get these sums in different bases. I think binary is a good one to practice. And then you start seeing, because it's just a yes or a no, right? Or an off or an on. I wasn't going to do anything higher than 10 today, but you may have seen like in base, visual arts majors, right? Graphic design, that colors are coded in 16 bits. So there's, A, B, C, D, E, F shows up, there's lots of fun little quirks when you do this arithmetic and these other bases here. Let's do some subtraction. I don't want to test our subtraction too much here. All right. So first I'm going to do something simple. All right. 2 minus 1 is 1, right? 2 minus 2 is 0. Oh, okay. All right. That looks fine. All right. Let's do another base 5 though. Let's do 2, 2. I like 2, 2 for some reason. And let's do 1, 3. I think we can agree that even if we don't know base 5, that the top number is larger, right? Right? There's more of the long packages, right? So there are more total pips, right, in this amount. But we got to subtract. You can't subtract. You can't do 2 minus 3, right? This isn't some negative number exercise. And so, this is, in my opinion, a flaw of how arithmetic is commonly taught, right? We say you got to borrow, right? You got to borrow. What are you borrowing, right? Any young person, cross that 2 out and put a 1 here. You're like, what did you borrow though? Did you borrow a 1? Well, no, right? The way we teach it for base 10 is you actually borrowed a 10 and you made this into a 12, right? But what are we borrowing for this example, right? This is base 5, right? So 5 smalls become a long. Well, this conversion goes both ways, right? A long can be 5 smalls. So if we, and I'm not going to use the word borrow, I'm going to use the word repackage, right? If I decide to repackage this as 1 long and 5 smalls, right? Those 5 smalls are what I'm adding to these 2 smalls. So total, we have 7 of those smalls. And now what's 7 minus 3? That's 4. Right? See how we still have to use base 10 as a crutch for this? That's how we think of it. But we're not borrowing a 1 because in our normal number system, borrowing 1 means make it a 10. You know, maybe I'll do a little demonstration right here next to it. So if we do like 52 minus 28, right? This is base 10. So many bases. We borrow, right? We say, oh, that's a 4 now, and this is a 12. Okay, well, but what did we really borrow? Right? We had a long, and we decided that's now 10 shorts, right? 10 of the little tiny packages here. And that is why we get to write 12, because 10 plus 2 is 12. But it looks like we're just moving a 1, right? And that's because base 10 is our native system. So the digits we're using are for base 10, and we get that nice ends in 0 conveniently, right? But in this case, right, when I borrowed a 1, that 1 long gave me 5 smalls. With the 2 is 7 total, right? So instead of adding 10, we had to add 5. And then 1 minus 1 is 0 here. So then, you know, again, this is, you know, your roommate walks in, see you doing some math, you're like, oh, there's my good friend doing his math again. Oh my, what did he do? You know, I gotta talk to her mom. She doesn't know how to subtract. Right? What's going on? You say, oh, no. It's cool. It's base 5. Right? It's base 5. And they're like, you're telling me 13 plus 4 is 22? Where are they teaching you at Hartnell College? Yeah. So anyway, so I thought these were fun little demonstrations. Again, you know, we use binary frequently to represent a lot, particularly in computer science, right? We have base 16 or hexadecimal frequently. That means we have to add digits. So, you know, 3, 4, 5, 6, 7, 8, 9. Now we need a digit for 10, right? 11, 12, 13, 14, 15, and we stop because with the 0, that gives us 16, right? This, oh my gosh, you know, what's a plus a equal? You know, that's like blows your mind. That requires another presentation at another time. And also we do use base 8 kind of historically for a lot of things. I think we're trying to replace a lot of its use with base 16, but I've heard not all the time. So I hope that in essence, this has maybe given you some more appreciation for how our normal number, you know, our normal base 10 number system works, you know, particularly with how we're repackaging these numbers in terms of their tens. And then a lot of the rules that we have about our numbers is a quick, convenient, like, check for us, and isn't actually about the numbers themselves, right? It's about me, it's not about the number, you know. So I hope that this was interesting. And you know, if there's any questions, I guess we'll have some time for questions now. So it's supposed to be an hour long, right? So should I is it common to record the question period, or should I stop the recording?
Let's see. I think it'd be a good thing to record the questions, but if anyone has any in the comments, you could
Okay.
just put them there.
Yeah, I'll keep you all anonymous in the comments.
So if there are no immediate questions, I'd like to thank our speaker.
I'm curious as
Nicholas
to whether
Pasquale.
people were aware of the divisible by 3 rule. How many of us already knew that one?
Type in the chat
Yeah, type in
or
the chat
say out
if
loud.
you knew. Yeah, put in the chat if you knew the divisible by 3 rule already. I was curious. I would like to know. And yet it's so simple, right? Like, what are they doing? What were they doing with us in elementary school? I didn't know it until I was in college. I took a class called problem solving in mathematics for my bachelor's degree, and we did a lot of stuff like this. Yeah, but yeah, I had no idea. Yeah, it was great to be here. Thank you for having me, Math Club, and you know, keep up the good work with building student community during these Zoom online pandemic times, and of course I enjoy our Discord channel. So hopefully I'll see you soon, in a future semester. Oh. We had a question in the chat. Are there other division rules? There are other division rules for 4. Let me share my notepad, I guess. For 4, right? If like I'll give you this number. I know this number is divisible by 4 because the last 2 digits are divisible by 4. Notice that when we had divisible by 2, right? It's only the last digit we need to check. Right, I'll change that number. And actually you can expand this a little bit. For divisible by 8, it's the last 3 digits that have to be divisible by 8. And the reasoning for that is because 100 is always divisible by 4. So it's just up to the 100th place that you need to check. Everything after that is a multiple of 100, right? And same thing here, 1,000 is divisible by 8. So you only have to check up to the 1,000th place. Everything else is just a multiple of 1,000. Right, so yeah, pretty cool.